Today we're going to start talking about scheduling. We're going to start off with the elements of a scheduling problem and then look at how this connects to graph theory and put it all together. So the first element of scheduling are the processors. The processors are workers who are going to carry out some task. And the workers could be humans, they could be computers, they could be robots, they could be any of those things. And when we talk about the processors, we are going to use the notation P1, P2, Pn to note our processors. So we would have n processors. And we are always going to assume that n is at least 2, because if you only have one processor, think of it like one person is doing all of the tasks. That's a very boring project to think about. So we are only looking at situations where n is at least 2. Second element of scheduling are tasks, which are units of work that cannot be broken up into smaller units. So think about if your project is writing an essay. You could say that write an essay is one task. Or if you chose to break that up, you could break it up into write your thesis, write your outline, write your rough draft, write your final draft, and break up the task of doing an essay into 4 smaller tasks. So however you decide to label your tasks, whether you're looking at fairly large chunks or whether you're looking at smaller chunks, that's fine. But the tasks are the things that you have to do. We are going to use capital letters for our notation here. So we could talk about task A, task B, task C, etc. Or we could use abbreviations or initials. So we could say if you are looking to divide up chores between yourself and your siblings, you could say that wash dishes is one task, clean toilet is another task, etc. Now, every task can be assigned to one of 4 possible states. A task could be completed, which is pretty self-explanatory. It's done. It could be in execution, meaning that it is currently being carried out by one of the processors. So if your brother is currently washing the dishes, then that task would be in execution. The third task would be, or the third possible state for a task would be ready. If a task is ready, it means that it has not started yet, but you could start it at any time. So if you could start cleaning the toilet at any time, but you haven't started doing that yet, that task would be ready. The final state is ineligible. That means that this task cannot be started yet because some other task that has to happen first has not happened yet. So if one of your chores is to do the dishes after dinner, but you haven't finished cooking dinner, then doing the dishes and cleaning up after dinner is an ineligible task because you haven't finished cooking and eating dinner, and those have to happen first. The third element of a scheduling problem are the processing times. So that is the amount of time without interruption that is required by one processor to complete a specific task. So how long does it take you to wash the dishes? How long does it take you to clean the toilet? How long does it take you to write an essay? And we have 3 assumptions about processing time. The first is that any processor can execute any task. So you and all of your siblings are all equally capable of cleaning the toilets. We call this the versatility assumption. The second assumption is that processing time is the same for each processor. So it takes you and your siblings an equal amount of time to cook dinner. This is called the uniformity assumption. And the last assumption is that once started, a processor will complete a task without interruption. So once you start washing the dishes, you're not going to get distracted. You're going to go ahead and continue and complete that task. And we call this the perseverance assumption. Now, there is one more aspect to scheduling problems, and that is the precedence relation. So this tells us what rules we have in terms of what tasks have to be executed before or after other tasks. So we're going to use the notation X and then a right arrow and then Y to tell us that X has to be completed before Y can start. So if you are writing an essay, you have to finish writing your rough draft before you can start editing and writing your final draft. So there are 3 different types of relationships that we can have between tasks. If tasks are independent, then that means neither X has to happen before Y, nor Y has to happen before X. They do not depend on each other. The other thing here is that the transitive property applies. If you remember back in algebra or in geometry, if X has to happen before Y and Y has to happen before Z, then that means that X has to happen before Z. That is implied. So in a list of precedence relations, you would see these first two. You would see X implies Y, or X has to happen before Y, and Y has to happen before Z. You would not see this third one, X has to happen before Z, listed in the list of precedence relations. The last situation we could have here is a cyclic relationship, where X is supposed to happen before Y, and Y is supposed to happen before X. If this is the case, then it is impossible to schedule these tasks because you cannot have X before Y and Y before X. So let's look at a situation here. You wreck your car and you take it to be repaired. There are 2 mechanics. We're going to label them P1 and P2. So they are our processors. And these 2 mechanics will be working on your car. They have 4 different tasks to complete. They need to do exterior body work, which will take 4 hours. Engine repairs, it will take 5 hours. Painting and exterior finish work, which will take 7 hours. And repair the transmission, which will take 3 hours. They're each going to work on tasks by themselves, so they're not working on the same task together. They're working on tasks separately. And the only rule we have is that A has to happen before C. So you have to finish the exterior body work before you can start painting and doing the exterior finish work. So we have 4 possible schedules here. This first schedule, processor 1 or mechanic 1 is going to start on task A, and then when they're done, move on to task D. The second guy is going to start with task B and move on to task C. And you can see that they are done in a total of 12 hours. This is a legal schedule because A is done before C starts. And we are going to say that the finishing time here is 12 hours because it took us 12 hours, or it took these two mechanics 12 hours to finish all of the tasks. So the finishing time is going to be the total duration of a project from start to finish. And we are going to use the notation FIN to represent the finishing time. Now, moving back here, looking at Schedule B, here the mechanics were able to finish in 10 hours, but this is not a legal schedule because A is not done before C starts. So even though this is a quicker way to schedule these tasks, it's not legal because it breaks the one precedence relation that we have. Looking at these last two schedules here, they are both done in 11 hours. And these are both actually optimal schedules. So we'll say that the optimal time is 11 hours. So the shortest possible time that we can complete these tasks is 11 hours. So an optimal schedule is a schedule that has the shortest possible duration and does not violate any precedence relations. The optimal finishing time is the shortest possible legal finishing time. And we said that we are going to use the notation OPT to indicate that something is an optimal finishing time. The last thing I want to talk about here is critical time. This is the absolute minimum. So if we look at our one precedence relation, which was that A has to be done before C starts. A takes 4 hours. C takes 7 hours. So we know that at a minimum, it's going to take 11 hours to finish these tasks. So the critical time depends on the tasks that have to be completed and the precedence relations. And it is the absolute shortest possible time that you can finish these tasks in. And one of the reasons that we know that schedules C and D on the previous slide were optimal is because those were finished in 11 hours, and that is our critical time. That is our absolute minimum. So that is our introduction to scheduling. We'll look in the next video at how this relates to graphs.